everybody. I hope everyone's having a wonderful day. So we're going to start with a new topic today. We're going to start talking about so-called minimum spanning trees. Now, before I can get to talking about what a minimum spanning tree is, what the problem we're going to look at is, I need to talk about a generalization of a so-called unweighted graph, which is what we've been looking at so far. We're going to talk about a weighted graph. So a weighted graph, G, has it where each one of its edges has a number associated with it. So this number might be an integer, it might be a rational number. Some you might, if you want to imagine it as a real number, you can imagine it as a real number. The point is that each edge will have a weight. I'll denote this as W of E, where W is the weight function. So just to illustrate this, I've drawn a graph here. We're going to be pretty friendly with this graph for a little bit. And I'm drawing out the adjacency matrix if I ignored out the weights. So if I just ignore the weights on these edges, this is what the adjacency matrix looks like. So how would you accommodate for the weights? All you would do is you change each one of these ones to be the weight of that edge. And anytime you see a 0, its weight will be infinity. So along the diagonal here, those will all be infinities. Implying that if you were to somehow include this edge in, its cost would be infinite, prohibitively making it impossible to include it in some sort of metric where I have some finite amount. So this is so prohibitively large that I would never want to include an edge with this weight in it. You can define it in any other way, like for example, if you only know that the edge weights are positive, then you can maybe set these to be -1. Either way, it's a representation saying that there's no adjacency there. So in an adjacency matrix, you can just simply, when the classic sense, what you do is you just fill in these entries with the weights. I'm not going to do it here. I'll let you try that on your own. Another way is more generally, you just simply have an edge object for which each one of these positions would actually store a reference to, and each one of those edge objects stores the weight. Now, naturally, if you're thinking about how you do with an adjacency list, what you do is each one of the nodes in one of the lists in the adjacency list, you would just simply store this weight along with the edge object or the opposing endpoint. So what do I mean by that? When you scroll across a list, you get all the you can determine the incident edges. So if you just store it with the opposing endpoint, this would just be an additional attribute that the node would have and store. However, if you store an edge object, the edge object would be just simply storing its weight. You'll find very often in the coming lectures, I'll just make the assumption that you can access, if you have access to an edge object, you can get its weight. So the assumption I'm going to make is that this weight of the edge can be computed in constant time, assuming I have a reference to the edge E. So this happens very often. Whenever I compute the incident edges, I can get each one of the edges incident on a vertex. That means I have access to edge E. That's where it's oftentimes going to pop up. Okay? So this is what a weighted graph is. So you could say that the weight of the edge B and F, this edge here has weight 9 or cost 9. Sometimes you like to call them costs, sometimes they call them weights, sometimes they call them lengths. And likewise, from C to E, that is 6. Okay? So that's a weighted graph. Now weighted graphs, you might naturally ask, why are these numbers? Why do I care about numbers on edges? Well, you can think about these as many different things. For example, these could represent physical distances between locations. As in I think it was the second application I showed you in a lecture previously about graphs. That's one way you can think about a graph like this. That's what makes it interesting. If you think about geographical data, for example. Another way you can think about these as costs. So actually, before that, when you think about distances or potential costs, these are called often routing problems. So imagine I want to get something from B to D. I want to route through this graph from B to D. These are so-called routing problems. Now, You can also imagine this as a cost to transport something from a vertex to another vertex, where these edges represent the cost to transport it. So these are so-called transportation problems. A lot of these problems overlap, by the way. Likewise, you can also look at these edges as some sort of allocation. So, say I have this edge here. This represents some cost of something I need to assign. For example, this might be a shipment that needs to be allocated to maybe vertex B or vertex F. So the goal here would be then to assign this edge a direction. So these are examples of so-called assignment problems. So this is just assignment problem over a graph. So the type of characterization that I talked about here was a so-called orientation problem, where you have to direct the edges or orient the edges. There's many examples. So weighted graphs do have their place in terms of graph theoretic problems. So you can think of certain kinds of assignment problems on graphs. You can think of transportation problems. You can think of routing problems. There's many different kinds of problems. These are just small examples. The point being is that there's some way to formulate many different kinds of so-called optimization problems on weighted graphs, just like you can on an unweighted graph. So that brings me to talking about minimum spanning trees. So we're going to talk about minimum spanning trees. I'll refer to it as an MST. So what exactly is a minimum spanning tree? Now, we know what a spanning tree is. Remember, we said that's a spanning subgraph that it's a tree, right? It's a special kind of spanning subgraph. Remember, a spanning subgraph consists of all the vertices in the graph. So I'm going to make the implicit assumption that the graph is connected. However, many of the things I say are very easy to extend to other kinds of undirected graphs. So I'm going to assume that this thing is connected, and our algorithms require that they're undirected graphs. So, that being said, I want to define something here. So, we know what a spanning tree is. What I want to do is I want to talk about a so-called minimum spanning tree, which we can now define on a weighted graph. Given a connected weighted graph, graph G is equal to BE. By the way, when sometimes people write weighted graphs, they oftentimes include the weights as an extra parameter of the graph. I won't do that here, just to keep things simple. Some people write it this way, some people just say, oh, there's just some weights out there. I just want to point that out, just because I like to make sure that you're aware of how other people sometimes write these things. A spanning tree, a T, whose total cost, and this is, how do you compute the total cost of a spanning tree? You just simply add all the edges of the spanning tree. So I just simply, if I have each edge in my tree, so in the tree, I'm just going to sum over all of its weights. So my goal is to find one that is the smallest possible. So this is what a minimum spanning tree is. Just as an example, let me consider this graph over here. A minimum spanning tree in this graph would it be, for example, the following one. So first, can you show me where a spanning tree is? Well, I could simply just take this edge, this edge, that edge, and potentially this edge. That would be a spanning tree. It would have some total cost or total weight. So sometimes I'll say total cost or I'll say total weight. So all I do is I would just add up those edges. So I'll let you think about how you would add those up. I'm just going to draw out what the minimum spanning tree is because I don't really have too many people I can bounce this off of, fortunately. So the green edges I have here, these are the edges of an MST. And how would you compute its cost or its total weight? How would you do that? Well, you just add them up, right? So so sometimes people will write the total cost or total weight of this as the weight of T. So sometimes they write it like this, weight of T. What is that? So I just simply add these up. So I have 4 plus 3 plus 3 plus 5 plus 6. So let's do some jogging for the noggin. So I got 6 plus 4 is 10. Then I got 11. So the total cost of this tree is 21. This is the smallest possible one you can make with this graph in mind. So what is the minimum spanning tree problem then? So this is the problem we're going to study. So the MST problem is as follows. So we're just going to compute an MST T of G, assuming that I'm given such a graph. So remember, these are undirected graphs that we're talking about. So I'll just explicitly put it here, undirected. So remember, whenever I don't specify anything, just assume the graph is simple and it's undirected, okay? So what is our goal? Just to create one of these. Okay, so that's the game plan. Now, I mentioned that this is an optimization problem. We haven't really talked so much about those. So I want to talk about that now. So in an optimization problem, you got to think about each problem instance. Remember back to the beginning of this course, I talked about problem instances. So I give you some input, so as part of an instance, and your goal is to find a solution. Now, in an optimization problem, instead of thinking about it in terms of, oh yeah, it's either the solution or not the solution, there's only one answer. Instead, you got to look at it like there's potentially many possible, feasible answers. However, there may be some that are very special called optimal solutions. These are the ones that minimize or maximize the goal of the problem. So we'll have some goal. In our case, this is a minimization problem. And the goal is to find a spanning tree whose cost is as small as possible. So this is a minimization problem. A feasible solution to this problem, meaning one that for which it follows the rules that it's a spanning tree, is very simple. You just give me one of these spanning trees, and each one of them has a cost, right? Or a total weight. So your goal is to give me the spanning tree that has the smallest possible weight. So any such solution is called a feasible solution. So it means you follow the rules of the problem. So it's not necessarily the optimal answer, but you follow it. But the ones that have the smallest cost, they're called an optimal solution. Where its value is the optimum, or optimum. So in our case, we have a minimization problem. Any spanning tree is a feasible solution here. It follows the rules of the problem. We want to find the minimum spanning tree. So these would be the optimal solutions that we're looking for. So our goal is to design an algorithm that computes an optimal solution for our problem. Can you see that every optimal solution is a feasible solution, but not the other way around? Okay, I'll let you think about that. But the point is that every optimal solution must be feasible because it's a spanning tree, right? So, why would you want to study this? So, it has natural applications in things like network design. So what do I mean by this? I'm thinking of things like communication networks. And transportation networks. This is one classic application of this. So, as an example, you could think of efficient coverage. Efficient coverage of electricity. Over power lines. Or telecommunication lines. So when I mean telecommunication lines, I literally mean things like phones. So what do I mean? Well, the main motivation for solving this problem was for this latter one and some of the former one, depending on what part of the world you're talking about. So you could view this now. So I should mention that usually distributed electricity, so distributing electricity typically has a very tree-like structure. It's not very much of a surprise that when you build a network of power lines that are supposed to distribute to different sites, you can think of each one of these as some sort of site where there's some set of power lines, and each one of these lines costs something to build. So your job is obviously to connect all of the sites to some power or telecommunication grid such that you use the least amount of materials, or you can think of it as the cheapest cost to build them all. So that's the natural application of this, and that's actually the main motivation underneath this problem. Now, there are many, many other applications for this. So I should mention that the people that the original designers and discoverers of the algorithms for these problems were thinking about things like this in the earlier mid-20th century. So there's all sorts of different applications that you can think about. So some examples I won't talk about here are, for example, clustering. Minimum spanning trees pop up in all sorts of different settings. So don't underestimate this problem. Network design pervades many parts of computing, so ranging just simply from computer networks alone. So the point here is that this is a fundamental but classic optimization problem. So, that being said, I want to talk a little bit about the minimum spanning tree problem. Now, when people design algorithms for problems like this, what they do is they study the problem itself, and their goal is to try to expose some property of this problem, or some structure that is related to the problem, so that you can design an algorithm that exploits that property. That is a very classic way of approaching algorithm design, and it's pretty much par for the course. So oftentimes people tell you, hey, look, I just go to my computer and I code something up. That is not how algorithm design normally goes. And normally that is the last thing you do as a computer scientist. Normally what you do is you study the problem, you try to extract some structure or some property that problem might have, and beyond that, your goal is to try to exploit properties of that problem. So that's kind of the classic way of studying a problem in computing. So that's what a lot of people like me do. That's what a lot of people that do algorithm design. That's very much par for the course. So anyways, we're going to talk about a property of a minimum spanning tree. So the big thing here is that when we study and design algorithms, our goal is to not just simply say, hey, look, I cooked this thing up, it works, I believe. As a computer scientist, your job is to say, hey, look, I discovered this property of this problem, and then my algorithm is going to try to exploit that property so that I know my algorithm is in fact correct. So let's talk about a property that's going to kind of form the bedrock of both the algorithms I'm going to present to you today. So there's a property called the cut property of minimum spanning trees. It's stated as follows. Let me just state it first, and then I'll explain, and then we're going to do the proof. So consider any weighted connected graph weighted graph G is equal to VE, where V1 and V2, which I'm going to define in a moment, are two non-empty sets of vertices of V with no common vertices So in particular, I should be very careful here. What I'm saying is that that we're talking about a partition of the vertices of V. So what I mean by partition, so I give you the set of vertices, I can split it into two sets. One is called V1, the other one's called V2. So there's no overlapping elements. That's what I mean by a partition. So let edge E equal U comma V be some edge. So let edge E U equal U comma V be some edge in G with least weight where U is in V1 and V is in V2. And the claim is the following. There is a MST that contains E. So that's going to be the claim. So I have two sets of vertices. These are going to be non-empty, meaning that there's going to be some vertices in V1, and then there's going to be the other vertices are all going to be in V2. So here's sort of the picture I want you to have in your head here. And I'll add more details to it as we do things. So I have two sets of vertices, V1 and V2. Now, there might be a whole bunch of stuff going on in this part of the graph. And there may be all sorts of things happening in this part of the graph. The point being is that there's some edge, E. So this is edge E that crosses from V1 to V2 or vice versa. So we would describe what I've just given you as a so-called cut. So any edges that cross from V1 to V2 are called the cut of V1, V2. So edges, we would often say, so if I say edge E, it goes from V1 to V2, then we would say that E is across the cut of V1, V2. So I must stress, now this is the most important part that I want you to notice, is that obviously there's going to be other parts of this graph that exist. Now I haven't really drawn these to be accurate, but the point is that there may potentially be other edges that exist that also cross this cut. So they are also across the cut, V1 and V2. Now, This is going to play a big role in our proof. So let's talk about that. So here's the proof. So I'm going to give you kind of the game plan here. So I want to pull up edge E and take a look at it and see if it has any interesting properties. And then what I want to do is look at this cut that I have here. So all the edges that cross this cut. So they are across the cut. What I want to do is I want to look at these edges and see if there's any relationship they have with E. And is there anything I can say in relation to E and these other edges? And that's going to be what we're going to try to exploit here. So I'm going to say, let T be a MST of G. Now, you should notice that E, the E as in the statement here, if I don't include E in this, what should T look like? So imagine I give you some tree that doesn't contain E. What should it look like? Well, it's still a spanning tree, right? But what happens when I put E into this spanning tree? What happens? Well, I have some equivalent definition of a tree that says if I add any edge to my tree, because it's connected, that should create what? A cycle. It should create a cycle. So I say by one of the equivalent definitions of a tree, if T does not contain E, then its addition to T creates a cycle, and I'm going to call it C. So what I'm going to do is I'm going to call T prime this resulting graph, okay? So now let T prime be T plus edge E. Now, T was a spanning tree, right? So T was a spanning tree. It's not T was. It is T was a spanning tree. Was a spanning tree. So what? What does that mean? If it was a spanning tree, what can you say about these blue edges? Is there anything I can say about now something along with these blue edges? Because there's got to be something that connects all these vertices over here to those that are over here, right? Because it's a spanning tree, right? So what happens? Can any one of these be a part of this cycle C? The answer is yes, it can be. And in fact, it is. It's a spanning tree. So in T prime, there is some edge, and this edge is one of those blue ones. There's some edge F equal to U prime, V prime, along cycle C. It's along cycle C. Where it also has one endpoint in V1 and the other in V2. So F is one of these. Say this doesn't have to be the case for any graph, but F is, say, that one. Now, what do I want to say here? Now, I pick E to be the one with least weight from V1 to V2 across the cut. So I picked that one. But what does that mean? Well, since E has least weight and F is not equal to E, because they're not the same edge, right? F is not equal to E. What does that mean? Well, it means the weight of E has to be less than or equal to the weight of F, because this is a least weight edge that's across this cut, right? So it's either going to be the same weight as F or potentially smaller. Does everybody see that? So now this is where the neat trick comes in. I love this proof because of this neat idea. If one removes edge F from T prime, then what? So if I remove F, what should happen? There's these edges that are going to, remember, there's still a cycle going on. There's some cycle that kind of goes around and F is a part of the cycle. If I remove edge E, there has to be some path from somewhere on that cycle back to its two endpoints, right? What does that mean? Then that means that T prime is a spanning tree. And its total weight is no more than with T. So T was a MST, therefore, the resulting tree T prime is also a MST. And we're done. So all we did was I observed the properties of the spanning tree, and then I switch out F with E, and then I show, hey, look, it was a least weight edge here, so it means that it has to be also an MST, right? So there's another more deep way you can look at this result. Observe that all this means, and this is really what's going to be at the heart of our algorithms, is that I just need to find the least weight edge that goes from some vertex in V1 to another vertex that's in V2. If I keep doing this, I can ensure that I get an MST. So you're going to imagine that V1 and V2 might change in this process, or I might potentially consider parts of the graph as long as they are induced together as one piece. So you'll see what I mean by this in a moment. So what does the cut property imply? So if I have two sets of vertices, V1 and V2, and I consider all the edges of all of V1 and V2, then all I have to do is I just identify a least weight edge of some part of V1. So one of its endpoints is in V1, the other endpoint is in V2. Then I can compute an edge E. I can guarantee there's some minimum spanning tree that contains that edge. So our goal is just to find that minimum spanning tree. And that's going to be how we can design our algorithms. Now, I'm not going to discuss the proof of correctness of either algorithm I'm going to present to you here. However, in the notes, I present the proof of correctness of one of the two. You'll see very quickly that the cut property is quite closely related to how these algorithms are designed. So I'm not going to spend time on any proof of correctness in this case, because the proof of correctness really is just applying this over and over again using a very clever trick where you just assume you have some MST and you give the output of your algorithm, and you apply the cut property repeatedly to the supposedly better MST, and you can show that you can keep maintaining that every time you move over an edge from your graph, from your MST, the supposed MST that your algorithm produces, you can keep switching them out until you eventually get the one that's exactly from the algorithm itself, contradicting the assumption that yours wasn't right. It's a so-called interchange argument. So, let's talk about some algorithms. So, the first algorithm I'm going to talk about here, this one I'm not going to go as deep on. It's called Kruskal's algorithm. So here's the idea. Now you want to think about V1 and V2 here. So what we're going to do is I'm going to grow a forest of MSTs from, and I'll call them seeds, but these are really just vertices to get an MST. To get MST. So at the beginning of Kruskal's algorithm, every one of these seeds starts out on its own, and then what we do is we take from, say these are seeds of some sort of tree for which they all just sort of become one conglomerate organism. There are some trees that are like that, and our goal is to create such a conglomerate, okay? So here's the idea. So at the beginning, every vertex begins in its own cluster. I'm not really saying it more precisely. And each one of these is a disjoint connected component of the graph. And I'm going to put parentheses here. I don't have this in the notes, but I should point this out. I'll say on its respective subgraph. So each one of these is going to occupy its own little bubble or cluster. And what we're going to do is we're going to do the following. We're going to add a least cost or least weight edge that joins or merges two of these connected components. So I should be very clear. When I use the word connected component, I'm talking about with respect to the subgraph that are the vertices of that sitting inside that bubble or this cluster. So I'm not using this over the entire graph. The idea is that you have all these little pieces of the graphs. Each is a subgraph, and each one is potentially some, with respect to itself, is just sitting in its own bubble with some vertices at some subgraph where it's connected, okay? So I have some spanning subgraph that is growing inside of each one of these connected components. So I'm going to have a bunch of spanning subgraphs that are going to be spanning forests, and my goal is to create a spanning tree from these. So if that confuses you, just think of these as clusters of vertices where I'm going to grow a spanning forest. And the goal is to make a spanning tree from the forest. So maybe I'll put quotation marks around these if that confuses you. So I'm going to stop this process. when the number of edges added is n minus 1, which results in an MST. Okay, so you end up with an MST at the end of this. Now you might ask, how exactly does that work? So we're going to do an example. Let's do an example. You're going to find I'm going to use this graph a lot for the next little while. Sure, let's do... Sure, I'll label them with letters. Next time I'll switch them to numbers. So I have A, B, C, D, and E. And the weights are as follows. So anyways, we start off with this graph. Now what did I say over there? Each one starts its own cluster. So each one of these is going to start its own cluster. So we're going to be building a spanning forest. So we're going to come up with a spanning forest. So I say that you're going to select a least weight edge that joins or merges two of these connected, these clusters here. So what are you going to do? You pick a least weight edge. So you just look. So when you implement Kruskal's algorithm, so the actual statement of Kruskal's algorithm, you're going to make sure that all the edges are listed from smallest to largest. And then what you're going to do is you're just going to take the first of the least weighted edges that can connect two of these clusters together. So in this case, that's 1 here. And what I do is the following. All I do is now I take the two clusters and I merge them. So now my cluster has grown into one for which has two vertices. So notice that this is a span, with respect to this graph, so this subgraph, this is a spanning tree of that cluster. So if you look at this cluster, this is indeed a spanning tree of that cluster. The way you can look at the correctness, because I'm not going to talk about the correctness, is imagine whenever you have any one of these clusters, you can look at the subgraph related to the one with the least weight edge between two of these clusters. Look at it as V1 and V2. And you can see very naturally that the cut property allows you to guarantee that if I pick this least weight edge, I can get an MST at the end of this process because I'm producing an MST of this subgraph. So every time I just increase the size of the graph by including another edge. So let's do the next one. So what do we do? So I got 1, got 2, got 3, 3 and 2 and 4. Now, if there's ever a tie between the least weight edge, just pick any one of the two. So what I'm going to do is I'm just going to pick this edge right here. That's the least weight edge that can merge two of these clusters. So now I have these 3 clusters. Now next, what do? I picked another least weight edge. Which one is it? 2, right here, right? So now the vertices A, C, and D merge into one cluster. And notice that inside the subgraph here, this is in fact a minimum spanning tree for this subgraph. Does everybody see that? So now we're building our spanning forest. Now what do I do next? Do I pick this edge? No, because that would connect an edge between two vertices already in one of my clusters. What would that create? It creates a cycle. So we don't want to do that. So one thing that's neat and we get for free from the cut property is that whenever we pick edges from one side of the cut to the other, we don't create cycles. Because you'll notice that I never put an edge back towards another vertex in the same cluster. I only merge them, right? So if I merge this cluster with that cluster, I'm not going to add an edge back into the same cluster. It'll be some edge to some other cluster, creating no cycle. So in both the algorithms we're going to see, every single time you're just going to have it where you have some vertices on one side, you have vertices on the other side, which I'll describe oftentimes as a blob, which I'll talk about more next day. And what we'll do is I'll just pick an edge, and I can guarantee there's no cycle because we always want to pick so that we don't create a cycle. This is implicit in how we construct these clusters. Now, I haven't talked about what those clusters exactly are, which is why I've been a little hand wavy over there. So let's do this. So I don't pick this edge, I pick that one, right? That's the least weight edge. It's 3 versus 4. So I pick this one right here. And now my cluster consists of all the vertices in the graph. And now I have a minimum spanning tree. Does everybody see that? So whenever there's a tie break, you just pick any edge. Our cut property doesn't really it doesn't judge you. Just be consistent typically when you do this. So that being said, I want to talk briefly about this. I don't have this in the notes, but I should point this out. So those clusters over there, each one of them is a set of vertices. So each one of those clusters is a so-called disjoint set. So you create all your disjoint sets, and then what you do, so disjoint meaning that they don't overlap. And then whenever we merge two clusters, we perform what is called a union operation. So we take two sets, we combine their elements, and since this partitions, that word again, it partitions all the vertices into separate sets, they will not repeat each other. So you have union operations that bring the clusters together. However, every single time you need to identify a least weight edge from one cluster to another cluster. So, like I said, in Kruskals, you would sort them from smallest to largest, the edges, and then what you need to do is identify if there is an edge that goes from one cluster to another cluster. So you would use a find operation on such a data structure to do this. So these are often called disjoint set data structures, and the operations I'm talking about here are union find. So oftentimes if you're talking about this stuff, you talk about disjoint sets and union find operations. So that's all I have to say about Kruskal. So when we come back next day, we're going to talk about Prim's algorithm, which is the one we're going to focus on for next class. So I say thank you very much, and have yourself a beautiful day.